Let us see this problem. We are given a number n. Our task is to check if n is a prime number or not. A number is said to be prime if its only divisors are the number itself and 1. Let's see these examples. N is 13. If you see all of its divisors are 1 and 13 only. So it's a prime number. If you see 14, it has more divisors. 2 and 7 are also its divisors. So it's not a prime number. If you see this number 101, it has only divisors as 1 and 101. So it's a prime number. The first few prime numbers are 2, 3, 5, 7, 11, 13, 17 and 19. Please note that 2 is the only even prime number. All other even numbers are not prime because they are divisible by 2. And for a number to be prime, it should be divisible by 1 and itself only. And the number 1 is not prime. See, all the natural numbers starting from 1, they can be divided into two categories, either prime or composite, except the number 1. 1 is neither considered prime nor composite. Whatever numbers I have written here, all the filling numbers except 1 are called composite numbers. So the numbers which have other divisors as well, they are called composite numbers. For example, 4 is a composite number, 6 is a composite number, 8 is a composite number, 9, 10 are also composite numbers. But number 1 is neither prime nor composite. Now please pause this video and try to write down a function that takes a number n as input and returns a boolean value. It returns true if n is prime, otherwise it returns false. Let us first talk about a naive method to solve the problem. In this naive method, we explicitly check for n equal to 1. If n is 1, then it's not a prime number. For other numbers, we are simply running a loop from I equal to 2 to n minus 1. And for every I, we are checking if I divides n or not. If I divides n, then n cannot be a prime number, because for n to be a prime number, the only numbers that divide it should be 1 and n. And we have excluded 1 and n. We are running for other numbers from 2 to n minus 1. And if we find any of those numbers dividing n, it means n cannot be prime. So that's the simple idea. Let's see the execution of this idea for 65. We are going to run a loop from 2. For I equal to 2, we check, does 2 divide 65? No. Then we check for 3? No. Then we check for 4? No. When we come to 5, we notice that 5 divides 65. So when we reach inside this if condition, we return false. We say that 65 is not prime. So our output for 65 is no. Let's now see for 7. We are going to begin with I equal to 2. It's not dividing 7. 3, 4, 5, 6. None of these numbers divide 7. So when we come out of the loop, we return true. It's a prime number. So our output is going to be yes. We return true for 7. Let us now talk about worst case time complexity of this solution. The worst case is going to happen when n is prime number, because in the worst case what will happen, you will check for every I and you will never find I dividing n. So you will never go inside this condition, you will come out. For example, 7. So when n is 7, we run this loop 5 times. 3 plus 2, 5 times. So when you have a prime number as input, it's going to run n minus 2 times. So we have an upper bound on the time complexity as big O of n. Big O of n is the time complexity. Please note that it may take constant time as well. For example, if you pass an even number, it's going to return false in the first iteration itself. For example, if you pass n equal to 8, you will begin with I equal to 2 and you will check if n's remainder with I is 0. So you get remainder 0. So you will return false. So it's going to do only one iteration in this case. So it may even take constant time. But an upper bound is big O of n, right? N is an upper bound. It's going to do n minus 2 iterations in the worst case. We can optimize this solution to time complexity big O of square root of n. Now please pause this video and try to think of a solution that works in this time complexity. Let us now talk about the idea for the efficient solution. The idea is, if I write all divisors of a number, I can notice that these divisors always appear in pairs. For example, divisors of 30 are 130, 215, 310 and 56. If you see this pair 215, If you divide 30 by 2, you get 15. And if you divide 30 by 15, you get 2. That's how we have formed these pairs. Divisors of 65 are 1 and 65 and 5 and 13. Divisors of 25 are 1 and 25 and 5, 5. So every divisor x of number n is going to have a pair y such that n divided by x is equal to y. Right? So if xy is a pair, then we can write x into y equal to n. And if x is smaller than or equal to y, mainly I have considered the smaller divisor of the pair, right? If I take the smaller divisor, then I can say x into x is smaller than or equal to n, right? And which means x is smaller than or equal to square root of n. So the idea is not to check from 2 to n minus 1, but to check from 2 to square root of n. And why do we need to check only till square root of n? See, if there is a divisor y, right, which is greater than square root of n, then this divisor is going to have a pair x, which is going to be smaller than or equal to square root of n. So I don't need to go beyond square root of n, because even if there is a divisor higher than this divisor is going to be having a pair, and I must have found that pair because I'm traversing till square root of n. So the idea is start from 2, traverse till square root of n. If you find a divisor, then you have the number not prime, otherwise you have the number prime if you never found a divisor. Now please pause this video and try to implement this optimized approach. Here is implementation of the efficient approach. The code is same in both C++ and Java. The only difference that is there in Java is we need to replace this bool with boolean. So in this implementation, we are mainly checking for every number starting from 2 to square root of n. And if I find any number that divides n, we say n is not prime. And if we do not find any number, then we say n is prime. So we begin a loop with I equal to 2 and we check while I into I is smaller than equal to n. So rather than writing I is smaller than equal to square root of n, I have written it other way, I into I is smaller than n. So while this is true, we check if n is divisible by I. If it is divisible, we return false, it cannot be a prime number, otherwise we return true if we come out of the loop. So when your n is 65, you are going to begin with 2, then you are going to go to 3, 4, 5. At 5 you notice that it's divisible by 65, so you return true. When n is 37, you begin with 2, you go to 3, go to 4, go to 5, go to 6 and you stop at 6, right? Because 7 into 7 is 49, which is greater than 37. And you can notice that how many iterations we are saving. In the naive method, we were running from 2 to 36. Here we are only running from 2 to 6. The time complexity of the solution is big O of square root of n. We can clearly notice it. We are running a loop from I equal to 2 while I is more than equal to square root of n. We can further optimize this solution. Now I am going to talk about further optimizations. Let us now get an idea for more efficient solution. If n is large, then square root of n can also be a big number. And in the previous method, we were running a loop from 2 to square root of n. And we were checking for every number if it divides n or not. We can save many of these iterations by adding 2 extra checks. The extra checks are, if n is divisible by 2, then it cannot be a prime. We need to have a base case or a corner case to handle the only even prime number, which is 2, right? Apart from 2, all the other even numbers are composite numbers. They cannot be prime. So if I add a check for n divisible by 2 or not, I can save many iterations. And if I also add one more check, if n is divisible by 3 or not, then also many iterations can be saved. Let's see how. See, if I have already checked that n is not divisible by 2 and n is not divisible by 3, right, then only I proceed to this loop. Because if I find divisible, I can immediately return that this number is not a prime, leaving the corner cases aside when n itself is 2 or n itself is 3, leaving those cases aside. So if I checked for these two things, I can save many iterations. If I checked for divisibility by 2, then I don't need to check for divisibility by 2. I don't need to check for divisibility by 4 also. Because if anything which is not divisible by 2 cannot be a divisible by 4 also, right? So we don't need to check for 4. Because of the same reason, we don't need to check for 6, don't need to check for 8, don't need to check for 10, 12, 14, 16. 18, 20. So all the even numbers can be skipped. We can reduce the iterations to almost half. Now if I check for n equal to 3 and divisibility by 3 also, then I don't need to check for 3, don't need to check for 6, don't need to check for 9, don't need to check for 12, don't need to check for 15, 18 and 21. So I only need to check for the numbers 5, 7, 11, 13, 17, 19 and so on. Now please pause this video and try to implement this idea. Here is implementation of the more efficient approach. So first thing we do is we check if n is 1. Because 1 is not a prime number, we return false. Now we are checking for n equal to 2 and n equal to 3. Why are we checking now for these two? Because we have a condition which checks if n is a multiple of 2 or n is a multiple of 3, then return false. Why are we putting this condition? To do the optimizations that we talked about, right? To skip many iterations. And when we are doing this optimization, we need to ensure that we return false when n is 2 or when n is 3. Because if I pass n equal to 2, then this condition will fulfill and it will return false, right? So we explicitly check for n equal to 2 and n equal to 3. If n is 2 or n is 3, we return true. In other cases, if n is a divisible of 2 or n is a divisible of 3, then it cannot be a prime number, right? Because once we reach here, we are sure n is neither 2 nor 3. After we have added these base cases, in this implementation, you may notice that we are skipping many iterations. First of all, we are beginning with I equal to 5. Now, we are incrementing I by 6. Not by 1, right? We are simply jumping many numbers and incrementing I by 6. And what are we checking? We are checking if n's remainder with I is 0 or n's remainder with I plus 2 is 0. If any of them is 0, then we return false. Let's understand with this example. Say n is 121. So you will begin with I equal to 5 here, right? Because none of these cases will be true, right? It's not a multiple of 2, not a multiple of 3. When you begin with 5, you are going to check if 121 is divisible by 5 or if it is divisible by 7. If it is not divisible by any of those two, you will move I equal to I plus 6. So then you are going to try with 11. Now you are going to try 121. Is it divisible by 11? Yes. So you are going to return false. You are going to say 121 is not a prime number. Let us see 1031. We begin with I equal to 5. Right, 1031 is a prime number. So we are going to check with 5 and 7. It's not divisible by both. Then we do I equal to 11. It's not divisible by 11 and 13 both. Right, when I is 11, we are going to check with 11 and 13 both. Then we are going to come to I equal to 17. We are going to check for 17 and 19. Then we are going to come to 23. We are going to check for 23 and 25. Then we are going to come to 29. We are going to check 29 and 31. It's not going to be divisible by any of those numbers because it's a prime number. We don't proceed further because the next number after 29 is 35. And 35 into 35 is greater than 1031. And now you can notice that instead of running from all the numbers from 2 to square root of n, how many iterations we are doing? We are only doing 5 iterations of this loop. So we save a lot of work with this more efficient implementation. If you take a closer look at this implementation, you can notice that this implementation is almost 3 times faster than the efficient method that we just discussed. We are incrementing I by 6 in every iteration, and in every iteration we are doing 2 divisibility checks, right? So we are mainly doing 1 by 3rd work compared to the previous solution where we were incrementing I by 1 and we were going from 2 to square root of n.